Okay. Hi, everyone. Thanks for being here. My name's Arnaud. This is Karl. We both work on the RabbitMQ team at VMware, and today we'll be speaking about streams. So we'll talk about the origins of streams, the very beginning, and then we'll focus on a couple of features, and especially a new one, filtering in RabbitMQ 3.13, and then we'll talk about the future for streams. So our replicated log type data structure. So that's a common abstraction in the industry, and we thought it would be a great addition to RabbitMQ so that we can expand the use cases that can be handled by the broker. So we had queues since the beginning in RabbitMQ. They have destructive consuming semantics. They are sophisticated, have a lot of features, but sometimes they are not just the good fit for some use cases. And streams are very different from queues. They have non-destructive consuming semantics. When you read messages, you don't remove them. And many readers can read the same messages at the same time. Streams are simpler than queues in their design and in their features. They are more opinionated, but they have sweet spots. There are things where they are just really good at. And they really complement queues in RabbitMQ. So that's why we introduced them. And now I will hand it over to Karl, who will speak about design and prototyping for streams.
Thank you. Is this mic working okay? Yeah. Okay. So yeah, I'll speak a little bit about the design and prototyping of RabbitMQ streams. So we knew we wanted this thing. And at this point, we already had quorum queues. And quorum queues, as many of you, I'm sure by now, are aware, are implemented on top of Raft using our RA library. And Raft is implemented as a replicated log. So it made a lot of sense for us to try to implement a stream queue type data type on top of our Raft implementation at first. So that's what we did. We wrote this RFC in November 2019. That's roughly when we started that. We made an implementation using RA, using a very simple state machine that quite simply exposed the Raft log for consumption and reading as it is. And it did work. It worked reasonably well. We integrated into RabbitMQ as a prototype integration. And it did manage to provide these new message access patterns that we wanted from our stream. So non-destructive consume and replay features and all those pretty good fan out, that kind of thing. But we tested it, and we obviously, as you do, you test the performance and the throughput that you can get out of this, and it was pretty good. We only tested it with the AMQP 091 protocol, which has its own set of overheads, being quite an old implementation and so on. And it did perform better than the other queue types, better than quorum queues, better than classic queues, but the performance was very far from what you would call a feature. Right? It wasn't anywhere near what sort of other competitors in the space were doing. I won't give you numbers because I can't remember them, but that's roughly the story. So we decided to make a dedicated replicated log implementation because we always need another replicated log. And we implement that as a library called Osiris. So Osiris, from Egyptian mythology, sort of either killed or took over the throne from Ra, the sun god. And so it's a little bit of a dig back at the original prototype in that name, a bit of a joke. So this particular replicated log design took a lot of inspiration from Raft. That would make sense. It's familiar to everyone. It was familiar to me. So it's a leader-follower approach. So you write to the leader, and then it gets replicated to followers. Internally in Osiris, they're called writers and replicas, but that's by the way. We'll call them leader and followers or replicas from here on. We decided to go for a quorum system because, again, it was familiar from us from quorum queues, and it has a lot of benefits that we wanted out of our replicated log. So obviously, a quorum system can handle the failure of a replica without even noticing. As long as you still have a quorum of members available. But another benefit is that the latency is not affected by the slowest replica. So in a system where you have to have acknowledgements from all your replicas before you commit an entry, the slowest replica decides the latency of your commit. And at least we can cut out the slowest one, so we get the second slowest instead. And we're also less reliant on failure detection. This one is an important one for me. I don't like failure detection. I think it's hard or impossible, one or the other, to do well. And obviously we need failure detection if the leader fails, but for the replicas we don't need to do anything. They just fail. And we deal with that in another way. Another upfront design decision that we decided to do is to use a dedicated TCP connection for the data replication part of Osiris logs. So when you spawn a replicated log, you spawn a writer or a leader and say 2 replicas, and each of those replicas will negotiate a connection, a port, and all that stuff, and set up a dedicated connection and start pumping data, only the log data. So we were able to use the send file syscall in order to avoid the kernel, userland kernel hop in order to put data on disk, or in the page cache most likely, on disk onto the network and replicate it. So that was a conscious decision that we took very early on. Another big call, in my opinion, that we took early on is that we weren't going to f-sync the data like we do for quorum queues. So quorum queues are Raft based. The Raft protocol requires you to durably persist entries before they are acknowledged. I think with replicated log like Osiris, you need to sort of loosen that requirement a little bit in order to provide the other non-functional requirements that you want, like performance and throughput. So there are many competitors that don't f-sync before they're acknowledged, so it should be reasonably okay. There's probably a whole, at least 20-minute, if not 2-hour talk on the implications of this little decision, but we won't have time for that, so maybe I can cover that some other day. So we wanted to evaluate what kind of throughput we could really get through this Osiris system once we've written it, which didn't take very long. And we wanted to bypass the AMQP 091 implementation in RabbitMQ in terms of the external protocol. So we wrote a dedicated prototype server just sitting on top of Osiris called the Osiris server. That's Arnaud's work here, and it contained an early version of what later became this dedicated stream protocol for RabbitMQ. And it was pretty soon we could establish that we could achieve something like 10, 20 times the throughput of the Raft-based prototype. And later tests, that was set up, just right. We were able to saturate both disk and network using this method. So it was pretty easy for us to make a decision to decide to sort of proceed with the implementation of RabbitMQ streams using the Osiris library rather than Ra. And we really felt that we managed to deliver on the throughput as a feature by then requirement and sort of been a missing piece in RabbitMQ for quite some time, being really able to access that sort of top-level throughput rates that fewer than you think need. Okay, so that was sort of the history. I'm also going to cover a little bit about, what do the internals of a stream look like, and what sits around a stream in order to deliver the feature in RabbitMQ. So an Osiris log, a replicated Osiris log, is what we call a stream in RabbitMQ. So stream in RabbitMQ is a first-class entity as part of RabbitMQ core. An Osiris log is a single replicated log. It consists of one or more segments, so they are files on disk, and each segment also has an index file, which is used to enable us to do fast seeks throughout the stream, and if you decide to read from a given time date, it's relatively speedy to do so. Each entry that's written is assigned an offset, so it's a sequence number. And when we write into Osiris, the entries are dynamically batched into what we call chunks, which are really batches, but whoever awkward person that actually wrote this code decided to call them chunks because feeling that batches are a little bit of an overloaded term, and maybe it will be needed somewhere else in the system. I'm still standing strong by that decision. I like the term. And the number of entries I sort of written in each chunk depends very much on the ingress rate. So we get some messages, we start writing them to disk, and whatever messages arrived whilst we were doing that forms the next chunk and so on. So there's no artificial latency, but we do batch as much as we can. Typically, we've never managed to batch more than 2,000 small messages into a chunk, but typically it's much, much less than that. Each chunk has a chunk ID, and the chunk ID is the first offset in the chunk. So if you got, if the last offset that you wrote was 1,000, you get a 10-message chunk. The chunk ID is 1,001, not 1,010. Osiris logs don't just contain message data. They also contain, we also decided to embed consumer and publisher tracking information into them because they're going to go with them, and we want them replicated, and we want them available when we fall over to a different replica. So they're written to the stream as well. So there's deduplication sequence numbers for publishers, and consumer offset tracking is also stored in the chunk itself. And this is sort of more of a graphical representation. You've got multiple segment index pairs. Each segment contains multiple chunks, and each chunk contains multiple entries and a header and a trailer. The offset tracking stuff usually goes in the trailer. Just the point. This is why chunks are important, why I like the name. They are the unit of work in a stream. So when we write to the log, we write a chunk. When we replicate, we read the header of a chunk, and then we replicate the entire chunk on the network. It's what we deliver to consumers over the stream protocol. So we deliver the entire chunk, and then the stream client unpacks that and calls your consumer callback with each message in the chunk. And that's because of one of the reasons why we could achieve very, very high throughput is that this dynamic batching. It's what we commit. I already mentioned the chunk ID is what we commit. And each index entry points to a chunk. It just provides you with a little bit of details on the chunk, the location in the file, and so on. So chunks are important. So an Osiris log is a static thing. So you start it, and then it runs, and if any of the members fails, nothing happens. So you need something to coordinate all that. So we implemented a stream coordinator in order to do that, to handle all the additional bits that you need in order to provide a fully featured stream. So the stream coordinator is a raw machine, so it's based on the same Raft implementation as Cornfuse and Kepri. It's responsible for starting new streams, monitoring all running streams, and if a leader fails, it performs the leader selection logic, which is based on the data in the log, and it's also quorum based. So it will make a selection once it has a quorum of log tails available to it. It's also our sort of DNS, internal DNS. It provides the locations of streams and replicas, telling you what replicas are running, where, and what the internal Erlang process ID is. As well as that, it now contains the single active consumer state, which is important in the next exciting section that Arnaud will cover. In addition to that, we have the stream plugging, which is just the protocol implementation. As I said, streams are part of RabbitMQ core. They're a first-class entity. And the stream plugin is just the highly optimized, optimally efficient way to access streams. And now, back over to Arnaud.
Thanks, Karl. Okay, super streams. So how can we scale out the processing in streams? It's actually a bit, and optionally maintain message ordering. It's actually more complicated than we can expect. So if you spin up several identical consumers on the same stream, they're going to read the same messages and process your messages several times. You can do some parallel processing in a client application, but you need to multi-thread your application basically. But you are going to lose the message ordering. You can have some so we just figured that it will be easy to scale out processing by reusing stuff we already have, streams. And we have several streams. We can plug a consumer on each of them. And then this way we just scale out. And this set of stream is just a logical entity that we can call a super stream. So principle is quite simple. It's just partitioning in this case. We wanted this to be as transparent as possible for applications. We didn't want to have any details, implementation details leaking into applications, like even the notion of partition. We knew that we need to delegate some of the work to the client libraries, like routing, for example, finding the appropriate partition for an outbound message. And we wanted also a simple rebalancing protocol, easy to reason about when consumers are coming and going. So for the publishing part, it was not that difficult. And actually, if I remember correctly, we had support for SuperStream, at least for the publishing side, since the beginning in streams since RabbitMQ 3.9. It was just hidden and not exposed. Just a couple of commands in the protocol. So the application gets to pick the partition a message will end up in. So there's no routing happening on the broker side. So for example, you have messages. Each message can be from a given customer. You can choose to hash on the customer ID, for example, and then you will end up with all the messages for a given customer in the same partition. And this way you can process the messages for a given consumer in the publishing order. So that's one of the guarantee we wanted. message ordering within a partition. It gets a bit tricky for consumers. So the idea is that whatever number of consumer instances you have for your application, you want to consume from each partition. So here we have three partitions, so we would like to have 3 consumers at the same time, one for each partition. So the idea is to have usually the same number of application instances as the number of partitions, and make sure to coordinate these consumers so that there's only one at a time on a given partition. So we used again a feature that we had, single active consumer, and it will, in this case, make sure that only one consumer instance, for example, here for the top partition, the green one, only one is active, even if we have different instances with the same customer running, only one is active. So the takeaways on SuperStream is that they bring some complexity. So make sure to use them only if you need them, if you think that you reach the limits of an individual stream. And we chose a composed approach here. A SuperStream is not really a new entity. We built it on individual streams and on single active consumer, which is also a feature that is usable with an individual stream. And we try to make it as transparent as possible for business code. If we look at the API of the client libraries that we have, the publishing and consuming code is the exact same as without a SuperStream. It's just that we can have some logic, one-time logic that we can provide for routing and even rebalancing, but just in the configuration of your producers and consumers. That's it for the philosophy of SuperStreams. Now, a new feature in RabbitMQ 3.13, filtering. So this is for another use case. For example, when you have a consuming application that is interested only in a subset of the messages of a stream. The simplest way to do that is just subscribe and get the whole content, every messages of the stream, and filter out on the client side. But this way, you transmit all the data from the broker to the client. So we wanted, to have some first level of efficient filtering on the broker side to save bandwidth. So efficient means fast, but we wanted also this to be decoupled. We did not want to couple the broker and the messages. So no message interpretation on the broker side. So let's see how it works. Each message can be associated with a filter value. So in this case, we have a stream, and for each message in this stream, we have a given region for the message. So green for Americas, purple for Europe, and dark blue for Asia. So in this stream, we have a green message, and then a dark blue message, a couple of purple messages, and a couple of green messages. If we are a consumer, for example, we can be interested only in America's green messages, and we would like to get only those. So how does it work from the beginning? We have a publishing application. It will publish messages, and it gets to choose, again, the filter value for each message. The filter value is just a string. So here we have the publisher sending the messages over the wire, so a green message and a couple of purple messages, and they will be added to the stream. How does it translate into the client API? So this is an example of the Stream Java client API. we create the producer, so that's just the configuration. And we have this filter value method where we provide the logic to extract the filter value from the message. So in this case, we look up the region key in the application properties, and what's returned by the message is actually the filter value that will be associated to the message. So again, that's something that's a cross-cutting concern. You just, it doesn't change the way you publish messages, just how you configure your producer. On the consuming side, a consumer, when it's started, will get all the messages from the stream. Here we can specify with an extra value configuration setting that we want only messages with a given filter value. So for the consumer at the top, it just says that it wants only green messages, America's messages. And the broker will do its best to dispatch from the stream only the green messages to this consumer instance. And same thing for the consumer in the middle with purple messages and the one at the bottom with dark blue messages. It's not exactly how it works internally, but we'll see the details in the next slides. And this is basically the concept. So this way we save some bandwidth, but not by not dispatching all the messages. How does it work exactly? Chunks. Remember, a stream is made of files, segment files. Inside a segment, you have for the one in the middle, no green messages, so we should not dispatch it. And same thing for the last one on the right. We should not dispatch those two. How can the broker figure whether to dispatch a chunk or not, depending on the consumer configuration? So in the chunk, we added a Bloom filter. And the Bloom filter can say whether a given chunk contains a message with a given filter value or not. So imagine you're the broker, you're about to dispatch the first chunk on the left. You just ask the Bloom filter, are there any green messages in this chunk? The Bloom filter will say yes, so the broker will dispatch it. And then the broker moves on to the next chunk, the one in the middle. It asks to the Bloom filter same question, any green messages in there? And the Bloom filter says no. So we don't dispatch this one. We skip it and move on to the next one. And for the last chunk, the one on the right, no green messages, but the Bloom filter says yes. It's the way Bloom filters work. They are probabilistic. They can give false positive. That's how they work. They are super efficient in terms of storage, but they can give false positives. So in this case, we actually dispatch a chunk for nothing, but we actually saved a chunk. The one in the middle, we did not dispatch it. So it's not so bad. But we want only green messages in our consumer, so we need client-side filtering as well. So when we dispatch a chunk, we can dispatch unwanted messages like the purple one. So we will need to put some client-side filter logic so that we actually get only green messages, the one we expect. And it's not so bad if we dispatch a whole chunk without any green messages because we will filter them out anyway. Again, how does it translate into client side, into the client-side API? So here, this is when we define a consumer, and there's this filter method where we can specify the filter value we expect. So in this case, this is Americas, and this is what we enforce on the broker side with the filter, the Bloom filter, and so on. And we have this post-filter method where we can specify some logic to filter out or let only the messages we want pass through and reach the actual consuming code. Okay, that will be in the message handler method. So we need client-side filtering logic as well. But again, that's something that can be easily provided, pluggable, thanks to the client library. Good candidates for filter values, geographical locations, like in the example, categories of products, types of products, that kind of things are appropriate. Obviously, unique message ID is not a good value because it's just unique. Couple of examples. So the first one with a large number of small messages with high ingress rate. So high ingress rate means large chunks with many messages. So if we get all the data without filtering, it's 384 megabytes. If we filter on one value, it goes down to 273 megabytes. So that's 29% savings. It's not so bad. For the second example, a small number of large messages, low ingress rate, so small chunks with not so many messages. The whole data is 10 megabytes when you don't do filtering, and if we filter on one value, it's only 2 megabytes going to the consumer. So in this case, we save 80% of bandwidth. So filtering depends really on the use case. It really depends on the filter value cardinality, the distribution, and even the filter size that you can configure. Remember that when you use it, the filter value you specify for the consumer and the client-side filtering must be consistent. They must work together. And you can use Bloom filter calculators online to size the filter. So with the number of filter values that you expect and the error rate, number of false positives that you can afford, you can choose an appropriate value for the filter size, because we will end up with a filter which is pre-allocated in each chunk, so it can make your stream grow a little bit compared with no filtering. So you need to experiment, basically. And that's it for filtering, and I hand it over to Karl for the conclusion. Thanks.
Right, thank you. So what's next? Well, it depends. Is the answer to that. We have some things that we really wanted to work on, some data safety improvements around the leader selection process, because given some of the prior design decisions that we took, there are always additional work that you need to be doing, particularly to do with the leader selection. One exciting thing for me is we're working on making our AMQP 1.0 or AMQP support really first class, and that includes streams, so that you can use the AMQP protocol in order to access super streams and get all the features with the metadata links to tell you where streams are running and where it's optimal to connect, including offset storage, which you can't do at the moment. You can use streams with any protocol in RabbitMQ, but there's many features like offset persistence that you can't access right now. I'm not sure exactly when this will happen. It will probably be in 4.0 or after 4.0. But ultimately, we are user-driven. So yes, streams is very similar to other products out there, other competitors. in what it provides. But we are not into wholesale competitor copying. That's not something that we do. We're not beyond copying, but it will have to be a good reason. And that good reason is our users and how people want to use streams. Filtering came out of a conversation with the user. We already had the idea, but we didn't want to implement it because it would just be implementing it for the sake of us having the idea. But when this user talks, we felt that would really be a good match, and that's a really genuine use case. So talk to us. We're quite friendly. We are very friendly often. And I think we've really come a long way since 2019 in terms of streams. I think, streams, really good throughput, super streams on top of that. Filtering, I haven't seen that anywhere else. I think that's exciting. Micro streams, maybe you can call them. I don't know. But I think we've come a long way. It's really exciting actually making this talk because we've kind of realized what we've done. It's sort of like a little bit of a retrospective for us. So yeah, we'll what comes next is very much down to you guys. So thank you very much. Huh? Yeah.
Thank you, guys. Any questions? Wow. Okay, you.
Hello, thanks for your talk. What's the story on client-side libraries? What's it going to be in the future?
Arnaud, do you want to?
Yeah, I can take this. So for the libraries, we work on the Stream Java client, .NET Go. That's the one we are maintaining, and we also took over for a Python library, I don't remember, but we try to keep them up to date. So the latest is, for example, support for filtering. So it came first in the Stream Java client, and I think it's implemented in a couple of other libraries, at least .NET. So it's testable.
Yeah, we have a dedicated team for libraries, and they help out with a lot of the libraries. As Arnaud said, there's some Python libraries, there's Rust as well. So yeah.
Thanks.
Shovels are not officially supported, but they work for streams to regular queues. Will there be a similar thing for filtering?
For filtering, you mean support shovels with filtering? Well, that would be technically possible, yes. As long as you can access the appropriate configuration, which is an X header in AMQP, not Wine. So yeah, I'd have to look at it. It might already be possible. I think right now, shovels will connect to the stream with the next strategy. So any messages that are added to the stream after the shovel connects will be shoveled. But we haven't had many requests for anything else, but that certainly if that's something that someone needs, make a bit of noise.
Who else?
Regarding super streams, if I have more streams inside of it, like more partitions than I have consumers, will it instruct the clients to properly create new threads or new consumers in it to be able to handle it properly, or you can run the risk of having more partitions than consumers and piece of the partition dead?
So it's on that's the client library responsibility, but the libraries we maintain, they start as many internal consumers. That's a composite pattern, actually. So if you have 10 partitions, it's going to start 10 consumers, one for each partition internally. Okay, so even if you have one instance of your application, you're gonna consume from the 10 partitions, right? And if you have only 5, it's going to work as well, because each instance of your partition will have some of its own consumer assigned to a partition. So it's possible.
And then when we repartition and rebalance, then if the client library is working properly, it will change the numbers.
So we didn't add support to yet. We don't know if we're going to do it, to resize the number of partitions. So right now we will need to restart the applications.
The number of sorry, the number of consumers. Like if I elastically increase and then decrease, it will create new ones.
It will create,
destroy them. And like
you should close them and restart them, and it should work. But we can support repartitioning better, but it's just that you're going to lose one of the benefits of partitioning, which is, of superstreams, which is message ordering when you add partitions. So we did have some requests for this, but we need to discuss more if we want to support it.
Thank you.
Cool question.
Hi, thank you. You mentioned that the segment has chunks, and each chunk has header and a trailer. And also mentioned that the trailer is tracking some position of the consumer, or what? I wonder if that means the trailer is immutable.
The trailer is immutable. Yes, all data in the stream is immutable. Yeah. So the way the offset tracking works is that you send a separate command into the stream writer, and it will record that data in the trailer. Or if there's no messages coming in, it will create a new special chunk that you never see as a consumer. Yes, just track the current offset. So
is it a fixed size trailer, or?
It could become quite large if you have a lot of offset requests coming in. Yeah, that's true. But we do the batching. So including the batching, we will only, if there's more than one offset request from a single consumer, then that will only be written once. So
right. How is it different from the offset storage that you mentioned in the last slide?
No, that's the same thing. That's how it's implemented.
All right. Another question: How do you usually, or as a user, how do I usually balance between either creating a new stream or using the filter?
Right. Yeah. I mean, the filtering is such a new concept. I think for the use case that sort of convinced us eventually to implement this, it was very much a case where they had a sort of a single stream that would have a sort of a limited time workflow that would write into that stream. And in order to rebuild the state, it's almost like sort of like an event sourcing type of thing, right? You take all the events and you rebuild your latest state. And it was in order to do that specifically for a given workflow, you could then add filtering on top of that.
So that was it. But the folks are really friendly. Please approach them. There should be lots of questions. And yeah, let's clap again. Thank you.
Thank you.